Okay, so okay, this is Discrete Structures. My name is Professor Overton. This is generally a sophomore level class for computer science, a junior level course for computer engineering. Quick show of hand, who's computer science? Okay, majority of you. And computer engineering? Okay, just a few, okay. All right. Well, what are we going to be covering in this class? Functions, sets, relations, proof techniques, propositional and predicate logic, counting, and a few other things. A variety of other things. But those are the main 6 topics that we're going to be covering. Now, this is a kind of equivalent to, very similar to what the math department has as a course, abstract mathematics. It is mostly a mathematical course, not like algebra or calculus where you're dealing with equations and that sort of thing, at least not in the traditional sense. Basically, what we're doing in this class is mathematically formalizing common sense. For example, just as a simple example of that, the AND operation. If one element is true and the other another expression is true, then the result of the AND operation is also true. Okay, if either one is false, then the AND operation is false. This is common sense. This is not rocket science. This is just how we normally think. It's just mathematically formalizing it to form, so you can form arguments and even in some cases find new information based on mathematically formalizing knowledge and manipulating it using common sense operations like and, or, not. If this is true, then this is true. Conditionals, biconditionals, that sort of thing. So mathematically formalizing common sense. What do you need to know? You should take notes, ask questions, and I think most importantly, communicate with me. I will allow notes on quizzes and tests, printed notes, not if you take notes on a tablet, you have to print them out before class and use those on quizzes and tests. As you can see, I have the camera recording this. I record all my lectures. I post them on YouTube, usually that afternoon or the following morning. So if you miss a class or you want to go over a topic again, you can go to YouTube and watch the lecture over again. I do edit the videos, so the roll call is not included on the YouTube video. When the video is uploaded, I will put an announcement out on Canvas with the link. I will also be available outside of class. I am here most days, pretty close to 40 hours a week. The general rule of thumb is If my light's on in my office, at my office, I'm on campus somewhere. If the door's locked, I might be in class or in a lab or something like that. If the door's unlocked, I'm ready, there and available. If the light's off, I'm not on campus. But for example, right now my light is on, but the door is locked because I'm in class. But I am available. My official office hours are on at the end of the slides. But you can reach me anytime outside of office hours as well. What makes up your grade? 10% attendance, 20% quizzes, 25% homework, and 45% in-class exams. I might adjust that through the course depending on how people are doing on individual segments. If you're doing well on quizzes, but you're, as a group, not doing well with the homework, I might change those percentages around to help you guys out. But this is what I'm starting with. All right. What homework is there? Homework is assigned on a weekly basis. That's not exactly accurate. I wrote these slides last semester, and I changing things up this semester. Each chapter will have homework, and the homework will be due before class starts on the day of the quiz or test that covers that chapter. So each chapter will have a quiz or a test after it. Let's see here. What should you be doing this semester? Attend class. Getting a good grade is almost impossible if you don't attend class on a regular basis and keep up with what's going on, what's being covered, that sort of thing. If you must miss class, and I'll get to that in a little bit, for a variety of reasons, let me know if you have to miss. I'll help you stay up to date, stay on track, make up quizzes or tests, or if you have to go out of town, maybe take a quiz or test before you go out of town. That sort of thing. I'll work with you on that. Take notes. Taking notes helps you absorb the material. And you will be allowed to use those notes on the quizzes and tests. There's a lot of material. Like I said, this class should be a year long instead of just a semester. So there's a lot of material to be covered in just 16 weeks. And I don't know of any profession, job, whatever, that in this field that wouldn't let you have references. You would have the internet or books or whatever. So same as I have the same policy as that. You can have references to some degree. Your notes. There's just too much information to have to memorize it all. I won't ask that of you. Ask questions. If you do not understand a concept, ask questions, and I will try to reword it or express it in another way. If you don't ask questions, I don't know that I'm not getting the idea across. So it's important to ask questions and make sure you get the material while you're here in class, because watching if you think, oh, I'll just miss class and watch the YouTube video, you can't ask questions of a YouTube video. Why is it important to take notes? Processing. You have to process the information to translate it to your notes. When you're writing stuff down, you're taking stuff in visually and auditorily, and you're translating it into words on a paper or a tablet or whatever, or even if it's typing it on a laptop. Some processing is required to do that. That helps you absorb the material. Even if you don't, if you think you got the material, write down notes, throw them away on the way out the door. I don't care. That's up to you. But the process of taking notes helps you absorb the material, whether you refer to them later or not. Organization. How you organize your notes is going to be different from how your neighbor organizes their notes. So copying notes from your neighbor won't be as effective as you taking your own notes. Now, if you miss class and you want to, and you need to copy notes, that's understandable. But the organization, how do you feel the information should be organized so you can refer to it later in an efficient manner? And like I said, they will be, and the paper notes are allowed on tests and quizzes. So, like I said, if you take notes on a laptop, tablet, that sort of thing, print them out before class, before the test. Like I said before, what I will do this semester is allow notes. You will not be expected to memorize all the material. It's just, problematic and impractical for that. I don't know. There will be a couple of instances where you might need a calculator, but so calculators will be allowed for use on quizzes and tests, although very little of that will be necessary. And record the lectures, like I said. YouTube the next day, and I will be available. I only have 3 classes this semester, so most of my days are going to be in my office working on a variety of other things. But my primary job is teaching, so that includes helping students out. If you have a problem, you don't want to discuss it in class, whatever, you can come see me in my office. I'm usually on campus around 8 o'clock, 8 or 8:30 in the morning, and I'm here typically until 4:30 or 5 in the evening. So Monday through Friday. I am understanding of special circumstances, disabilities, sports, band, student organizations, travel to conferences, interviews. I understand things happen that you need to miss class. Do we have any band members? Yeah, okay, we've got a few. I know travel with the band is important. A lot of band members are scholarship students, so you got to go where the money is. Fulfill your obligation to the band so you can keep your scholarship and all that sort of thing, and stay in school. So, travel on band trips and stuff like that. I'll work with you. There's the recorded videos. Tests and quizzes can be made up. No penalty on that. Have any student athletes? Okay. Likewise, games, travel to games or events. Have can take its toll on your academics, but I'll work with you on that. Student organizations. I put that in there. I've never had anybody miss something because of like a fraternity event or anything like that. But if it happens, I'll work with you on that. Travel to conferences like BEA or NSBE. I highly recommend going to conferences. It's an opportunity to network, get job interviews, maybe job offers, that sort of thing. So, and internships. Get internships at various conferences. So I highly recommend, if you get the chance to go. There's a kind of a saying in academia and research: opium is good, not the drug, but OPM, other people's money. If you get to travel using other people's money, go for it. I did a lot of that when I was an undergrad. One conference I went to was in Africa, and I spent a week and a half in Africa on a conference, and it was an amazing experience. Jackson State paid for it, so if you have that opportunity, I would definitely take advantage of it if I were you. And of course, job interviews or internship interviews. If you have to miss for that, like I said, you got to go where the money is. So, if you need to miss class or something for a job interview, let me know, and I'll work with you on keeping you up to date and up to speed. Let's see here. Any questions about what we're going to be doing this semester? The syllabus is on Canvas. The way things are going to be presented, I'm going to basically lecture from my notes and use the whiteboard on the screen. But there are slides that go with the book that is associated with this course. Those slides are posted in the files section of Canvas. So you can download those slide presentations and follow along in that regard. It words things a little bit different than me. It might have a few more examples than I do. I'm trying to squeeze as much material, like I said, into 16 weeks as I can. So, the slides are there for you to look at your leisure for studying, that sort of thing. But I'm mainly going to be using the whiteboard for the lectures. Finally, I thought that this class was going to be 3 o'clock, so the office hours are actually going to be Tuesday, Thursday, 12 to 1:30 officially. But like I said, I'll be here typically 8 or 8:30 in the morning to 4:30, 5 o'clock in the evening. That's my email address and my cell phone number. Don't abuse it. I don't need to be called at 2 or 3 o'clock in the morning with questions about homework that's due in a few hours. Please respect, reasonable living schedules. Sleep at night, work during the day, that sort of thing. Texting is probably a better approach than actually calling, because I can respond when I'm able to, if I'm in class, that sort of thing. So, like I said, it's my cell phone. Just use responsibly. And that's it for the slideshow. And we're going to go ahead and start the lecture part of the course. Was there any questions about all that, or any comments or what have you? Okay, well, the first chapter of the book is Speaking Mathematically. First section is on variables. What is a variable? It is a placeholder. Using variables gives you the ability to refer to quantities unambiguously throughout an argument. So a variable can represent different things. It can be a statement, numbers, or Boolean expressions. So when do you use a variable? Well, you can use it when the quantity is unknown, might be several of them, or making a statement more general. Okay. So you use variables to when you don't know what the value is, like you would in a normal algebra or calculus class when you don't know what a value is and you're solving for that variable. You use a variable and you use it consistently throughout the argument or steps in the manipulation of that problem. A variable could be one of several or even infinite number of values. So, like a range of values, or turn the page. Like the quadratic formula yields two values. The x equals plus or minus the square root of blah, 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 so on down the line. It can represent two values. So you use the x consistently to find those multiple values. Some examples. Let's see here. Are there numbers with the property the sum of their squares equals the sum of the sum squared. That's come on now. The sum squared. How would you express that in a formula with variables? the sum of the squares, a squared plus b squared equals sum a plus b squared. So you're taking the statement and using variables to express it mathematically precisely, rather than the imprecise use of words. Or if you're if you have the statement, given any real number, its square is non-negative. So so with a variable, you would say, given any real number r square is non-negative, or is greater than or equal to 0, which is a true statement. Now you use these variables in various types of mathematical statements. One of the most important kinds of mathematical statements are the universal, the conditional, and the existential. Now, the universal statement is true for all elements. True for all. So, like the statement, the example I gave a couple of moments ago, for every real number r squared is greater than or equal to 0. It's for all real numbers. It is universal. A conditional statement, if one thing is true, then some other thing also has to be true. If true, then true. You might remember conditionals in programming, the if statement. If such and such condition is true, execute this block of code. That is a type of mathematical statement. An existential statement is true for at least one. So the first example I gave a little bit ago, does there exist a number such that the sum of the squares equals the square of the sum? If that statement is true, I haven't done the math and figured out whether or not it is true or not, then that would be an existential statement, because it's obviously not true for all real numbers. 2 squared plus 2 squared is not equal to 2 plus 2 squared, as an example. So existential is, it is true for at least one element with the There's at least one thing for which the property is true. So one out of the set if the existential statement is true. Now you can combine these types of statements into, for example, the universal conditional statement. A statement that is both universal and conditional. For example, for every animal A, if A is a dog, then A is a mammal. For every animal, universal. This makes it universal. And this here makes it a conditional. It is both. Now you notice we have the variable in there. So for every animal A, if A is a dog, then A is a mammal. Then we have the universal existential statements. Universal existential. The first part says that a certain property is true for all objects of a given type. The second part asserts the existence of something. So, example, every real number has an additive inverse. Every real number, universal, and there exists a additive inverse, just one, for each real number. So every real number, universal, has an additive inverse, makes it existential. See what I'm saying about what I was saying about mathematically formalizing common sense? I mean, these are, common sense statements that you know to be true, and just simple logic tells you that these things are true if you understand basic math or biology in the case of dogs being mammals. But it's formalizing it, giving it terminology that you can use in research papers, theses, dissertations, that sort of thing. But Now, these statements can be written in several ways, some formal, some informal. Like all real numbers have an additive inverse. That's kind of informal. A more formal way of saying it would be, for every real number R, there is a real number S such that S is an additive inverse for R. So, different ways of expressing it in English, but it all amounts to being the same, the universal existential statement. How can you restate the statement, every pot has a lid? All pots have lids. Universal existential statement. All pots have a lid. Unless you're in my kitchen where I've lost so many lids, not every pot has a lid. But that's another story. Then you have the reverse of this, the existential universal statement. Okay. Existential universal statements, the first part says that a certain object exists. The second part says the object satisfies a certain property for all things of a certain kind. For example, there is a positive integer that is less than or equal to all positive integers. This statement is true because the number 1 is a positive integer, and it is less than or equal to all positive integers. So, but there is a positive integer, makes it existential, and it is less than or equal to all positive integers, makes it universal. The existential part comes first, and then the universal part comes second. Let's see here. What about, there is a person in my class who is at least as old as every person in my class. Look at there is a person, existential, who is at least as old as every other person, universal, in my class. Also true. Somebody's got to be the oldest, so it's a true statement. You've all taken Cal 1, right? So you understand limits? Okay. Definition of a limit of a sequence. The limit of a of n as n approaches infinity is L. Can only be defined using phrases that are universal, existential, and conditional. For every positive real number e, there is an integer n capital N, such that for every integer small n, if small n is greater than n, then a sub n is greater than minus e and less than positive e. Kind of a mouthful, but it's mathematically formalizing that definition using universal for every positive real number e universal. There is an integer n existential. That's for every integer n, another universal. If n is greater than n, then conditional. That little blurb there. But yeah, you can tie the universal and existential statements together in a variety of different ways. It just makes it a little bit more complex and difficult to read when you use informal language. When you're using formal language with variables and that sort of thing, the variables make it easier to see a general form of an argument rather than being occupied with what individual statements mean and whether they're true and all that sort of thing. More examples will be coming of this later. All right. That was section 1 of the chapter 1, variables. The language of sets is section 2. If I'm recalling correctly. Use of the word set as a formal mathematical term was introduced by Georg Cantor in 1879. So it's not that old of a discipline, set theory and all that. It is a set is a collection of elements. All right. I have some symbols here. If X is this symbol of S, then X is an element of set S. Kind of a stylized E for element. It's an element of the set S. X is an element. S is a set. Generally, I've seen, I don't know if there's any formal rule about this or not. When you refer to a element of a set with a variable, you use a lowercase letter. For the set, you use an uppercase letter. That's just generally what I've seen. I don't know if that's hard and fast fact or not. But, and X is not in set S. So that symbol there indicates that the element S is not, X is not in set S. Set roster notation is used to write the elements of a set in curly braces. So That would define a set of the numbers 1, 2, 3, and 4, where the elements are the numbers 1, 2, 3, and 4. I say that because we're going to get to a little bit more elaborate things here momentarily. For large or infinite sets, you can do the ellipsis to indicate a string of numbers where you don't have to list all the numbers, say from the natural numbers from 1, 2, 3, 4, 5, all the way up to 100. You can use that notation, or you could end the set notation with the ellipsis to indicate that the set is infinite in size. The axiom of extension says that a set is completely determined by what its elements are, not the order in which they are listed, or the fact that some elements may be listed more than once. Okay? What does that mean? Say you have set A, 1, 2, 3. B is equal to 3, 1, 2. And C equals 1, 1, 2, 3, 3, 3. The elements of A, B, and C are the numbers 1, 2, and 3. Okay? Some are duplicated in C, but the elements still remain the numbers 1, 2, and 3. So the axiom of extension says these three sets are equal. Now, the only thing that you got to, I like to point out on this is this in C++ is a valid statement. It defines an array with those three elements in the array, right? This is a different array, and this is yet a different array. Sets are not like arrays in C++, even though the notation is the same mathematically versus programmatically. And we'll get into later on when we get into logic functions. I'll show you the difference in different notation depending on what field of study you're in. Ooh, tricky one. Is that true or false? It is false. The set of with the element of 0 is not equal to 0. This is a number. This is a set. They are not the same thing. So if you mean a set, use the set notation. If you mean a number, use the plain number. Don't confuse the two. Like I said, this is formalizing different concepts. Let's see here. How about that is allowed as well. You can nest sets within sets. It's kind of like having an array in C++. So this set contains two elements, the number 1 and the set containing the number 1 as an element. So you can nest sets. Now, some sets are special. R is the set of all real numbers. Z is the set of all integers. Q, rational numbers. And N natural numbers. Now you might, where they get the Z from for integers, I'm not sure. But the Q for rational numbers, think quotients. Every number is a quotient. Rational numbers. Natural numbers are 1, 2, 3, etc. You can also add a superscript. Yeah, superscript, such as R plus, Z minus, Q plus. Those indicate that those sets are only referred to the negative or non-negative elements of the set. So you got those commonly used sets. And special variables for those sets. Now, set builder notation is a way to express a set without listing all of its elements or using the ellipsis or that sort of thing. So let S denote a set. S equal to X is an element of S such that P of X so that means S equals the set of all elements being an element of S that satisfy the property P of X. So let's see if I have an example here of this. No, I don't. So let's say, let's just say, give an example. P of X is true if X is divisible by 2. Okay, so the set of even numbers would be the set X is an element of even numbers such that P of X is true. The vertical line means such that X is an element of even integers, such that P of X is true. So it's defining a infinite set in this case without using the ellipsis, just using a conditional. Then you have relations between sets. The most basic relation is the subset. If A and B are sets, sets A and B, A is a subset of B if all the elements of A are also in B. Okay, there's a line underneath that. So there's one. If that's not a C, that's a. Let me clean that up a little bit. It looks like a C, but it's a kind of a rotated U. But that indicates that A is a subset of B if all the elements of A are also in B. Now there's a slight difference between this symbol and A is a proper subset of B. A proper subset of B means that there is some element in B that is not in A. This is kind of like the less than or equal to sign. A can be equal to B and still be called a subset. This is more like the less than sign. All of the elements of A are in B, but there's some elements in B that are not in A. That's what a proper subset is. Now, just get some if people are still writing, I'm gonna hold off a little bit. But give some examples of some exercises here. There's some. Which of the following are true? 2 is an element of 1, 2, 3. Okay. Which ones are true and which ones are not true? What about the first one? True. Yes. Second one? False, because this is a set, not a number. What about this third one here? False. This is not a set. In order for it to be a subset of this one, this has to be a set. So the fourth one is true because the set of 2 is a subset of 1, 2, 3. The set of 1, 2, and 3. So little nitpicking, hair splitting, and that sort of thing going on there, but the fourth is true, yes. Because here you're comparing number versus set, whereas this is set and set. Yeah.